summer, which means that the output is going to be summation of all the input signals. So you can practically using registers, op-amp, and input sources, you can practically implement and weighted sum. And we went through the derivation already. Today, also I asked you to go through these exercises in the scribing. Today we are going to go through non-inverting operational amplifier configuration. So non-inverting operational amplifier configuration. So one thing, just a simple recap. Please pay attention, guys. A simple recap. Inverting operational amplifier, what did we do? So we had an op-amp. This is the inverting terminal, this is non-inverting terminal. Non-inverting terminal was connected to ground, and inverting terminal was connected to a register. And if we have input Vi, and the output is going to be taken from the output terminal. If these two registers RF we have here, RF and RI, then output is going to be negative RF over RI times Vi, which means that if the output, if the input is positive, output you will get the scaled version of the input, but it is going to be negative. If the input is negative, output is going to be positive with some scaled version. Did you guys understand? So if the input is positive, some value, some voltage, output is going to be negative with some scale factor. If the input is negative, output is going to be positive. If the input is positive, output is going to be negative with some scaling factor. You understand, guys? So output is going to be input multiplied by certain constant with opposite sign. That's it. Non-inverting operational amplifier, what you will have, non-inverting operational amplifier, you will have input to the positive terminal, and negative terminal will have a resistor there. I have this in the next slide. I'm just going to show you a simple difference here. If the input is Vi, output is going to be Vout. If the input is positive, output also positive. If input is negative, output will be negative. You understand? Only difference here is that you apply input to the non-inverting terminal, and here you apply input to the inverting terminal. That's why you get output, which is the opposite sign of the input. Here you get the output, which is the same sign as the input. Okay? And because it is amplifier, which means that output is going to be multiplied by a certain constant. Is that clear? Okay. So that's the main idea behind non-inverting operational amplifier. Non-invert, like why? If you look at this word non-invert, so it means that it does not invert. Okay, it does not invert the signal. So let's move on here. Okay, it doesn't matter. Here I drew. See the way I drew. I have non-inverting terminal connected to the input. Just to recap, this terminal, which you see plus symbol, is called non-inverting terminal, and this terminal, which you see negative, this terminal is called inverting terminal, and this is input, this is output. Input, this is input signal, this is output signal. Okay, non-inverting terminal is connected to the input. Here we have non-inverting terminal connected to the input. You see that? Non-inverting terminal is connected to the input. And yeah, non-inverting terminal is connected to the thing. Inverting terminal is connected to the output through a resistor. Inverting terminal is connected to the output through a resistor after. And another resistor is connected to the ground. So you can draw this non-inverting operational amplifier configuration this way, or author has drawn this way. So it doesn't matter. As long as you have the terminals correct, so you are in good shape. The main purpose here, we have the input signal, input voltage Vi, and we have the output voltage. Main purpose here is to find the voltage gain, find voltage gain AV, which is by definition output over output voltage over input voltage equals what? That's the main question. So what is the voltage gain? What is the gain of this operational amplifier? So that we can just replace this as a black box. So this is going to be gain AV, and input is going to be Vi, and the output is going to be VO. So inside this black box, you will see this operational amplifier with certain gain. Okay. So those who are taking mechatronic guys, you see the gain that we have in temperature sensor. The gain is implemented in temperature sensor. You will see many, see the temperature sensor that we have here. So this temperature sensor, the thermostat, this temperature sensor has some gain. In the data sheet, you will see that gain of, let's say, 10 millivolt per degree Celsius. So for each degree Celsius, the voltage generated by this temperature sensor is 10 millivolt. Okay. So this gain, the word gain, is implemented here. That's what we are trying to analyze. How we find this gain. So I'm not going to read my slide here. What I explained, they are written right here. Okay. So we want to find this voltage gain AV. But here I put GV, a closed loop voltage gain, with the same expression GV. Don't get confused. So GV, I mentioned in case you have many other circuit components other than just non-inverting configuration. In case you have many other circuit components and input is far from the non-inverting terminal, with the input you see somewhere here with lots of resistor network, then what will be the overall output and input ratio? That is going to be GV. But in this case, AV and GV is the same because it's a simple circuit. Now I have some steps, but I'm going to draw this circuit again and analyze so that you guys understand. And I'm not going to go through these steps. I did mention these steps, but I want you to understand. I want you to draw the circuit as well. So we have non-inverting op amp. So we have this is V out, this is positive, negative, and input right here, input, which is voltage source. So VI, and then this is connected to ground, and this is R1, this is R2, and this is the inverting terminal, this is non-inverting terminal. So from this circuit, all what we want to do is to find voltage gain AV equals V out over VI equals 1. So if you know this derivation, guys, it's a piece of cake for you to go through some examples. So here, I'll just give some numbers to this resistor network. For example, R2 equals 10K and R1 equals 1K. And VI is 10 volt. So what is the output? So if you know how I analyze this circuit, then it is going to be a piece of cake. So please do make sure that you draw the circuit diagram and analyze the circuit with me. Okay. So because ultimate goal is to find V out over V input equals, what is the expression here? Look. Because we have a feedback, part of the output is going to be pushed back to the input. And that will make sure that these two terminals have equal voltages, which means that they are virtually short. There is no connection, there is basically a short connection, virtually short connection between these two terminals. So you can think of this as a piece of wire. Clear? You can think of this as a piece of wire. I went through this in our last class. And then, because this op-amp has high input impedance, so therefore the current going through this terminal is going to be 0 ampere, and current going through this terminal is going to be 0 ampere. So no current will flow because the input impedance between these two terminals will be infinity, I agree. Okay. Now, I want to give the reference voltages to each resistor. So which way you want to give? Positive here, negative here, or positive here, negative here? Which way? It doesn't matter.
Positive to the left and negative to the right.
Positive left here,
Yeah.
positive here, left, negative to the right. That's how you want to give. It does, as I said, that it does not actually matter. So when you actually do the circuit analysis, it will give you the correct result anyway. And here, how do you want to put? Here, positive here, negative here. Okay, so I'm giving positive here, negative here. So which means that the voltage drop across R2 is going to be V2, and current, because I put this reference polarity like that, positive here, negative here, therefore current will go in this direction according to this reference polarity. So it is going to be I2. And because I put reference here, so it is going to be V1, and the current flowing through this R1 is going to be I1. So you can put I1 here. I1. Okay. Okay. Guys, look. You can think of this as a voltage source, which is V0. Okay? See the notation, guys. See the cursor, how I go, guys. You see no current is flowing in this direction, right? 0. And this guy said the reference polarity is this way, which means that the current is flowing this way, right? No current is flowing in this direction. Therefore, all this current, which is I1, is going in this direction, right? Right? Which means I put I2, which is the current flowing through this R2, is going to be I1. Right? Okay, I1. And let's say if call this R. Same current. So same current flows through resistors. What does that mean? That means these resistors are connected in series, right? These resistors are connected in series. If resistors are connected in series, they will have same current, right? They will have same current. So here, see, I have bunch of lights here. These lights are connected in series. So we have just only one switch. If you turn it on, all the lights turn on, and same current is flowing through all these lights. Okay, so which means that this circuit. Look at my cursor, guys. This circuit. Okay. This circuit is simply a series circuit. You can think of this circuit as this is V out, R2, R1, and this is ground. Do you see that? You go from here to here, you can think of this as this circuit. Now, I want to get the voltage. I want to get the voltage across R1. So what is the voltage across R1 here? I1 times R1, which is I2 times R1, same, right? Which is I. But don't you think that to get this voltage, you can simply apply voltage division principle here? Simply voltage divider, right? So V1 here is going to be simply R1 over R1 plus R2 times V0. Okay? So we have simply a voltage division principle here. So positive here, negative here, I put positive, negative here. So this V1 is going to be simply, you have simply a voltage division principle. Guys, look, because this guy said that I want to put positive here, negative here. And here I have positive, negative here. Okay, because it is the opposite direction, if you, a current is going this way. Okay, current is going to be according to my symbol. So this V1 is going to be simply negative with respect to the polarity, actual voltage source that we have here, which is output. Now I have another circuit. So I'm going to put different colors here. Okay, guys, do you see the input voltage here? V sub I. Do you see that? Positive here, negative here. I said that because of the feedback, and we said that op amp is ideal. These two input terminals are simply connected, virtually connected, short. So do you think that? So we have a voltage source here. We have a voltage source here which is positive, negative, V sub I. This is ground, and then we have basically a connection here. So it's a piece of wire, and then we have a resistor here. So which is positive here, negative here, V1, and then you have ground. Okay. So now you tell me what is the voltage across V1. So we have voltage source V sub I. If you apply KVL, here, so you have a voltage source and you have only a single resistor connected in series. What will be the voltage across that resistor? Set as a voltage source. That's what I was trying to get you, make you understand. So if you have a single light bulb and you have voltage source here, like 110 volt, okay, and you connect. So whatever current you produce from this source is going to be absorbed by this light source, okay, and this current times the voltage that you have here. The whatever power you have there, this entire power source is going to be absorbed by this line. So therefore, the voltage across this resistor is going to be exactly the same as this voltage. So what you have here, if you simply put a KVL here, so you have negative V sub I, negative V1 equals 0. So therefore, V1 is going to be negative Vi. So you can write here in the loop connecting, you can write it down just for simplicity, loop connecting. V naught R2 R1. We write V1 equals negative R1 over R2, R1 plus R2 V naught. And if I said here you put positive here, negative here, that way it's much easier, but because I put the opposite way, so that's why I have to maintain the polarity accordingly. So therefore V1 is going to be negative with respect to this point. Actually, with respect to this point, this voltage of this point is going to be negative. From the circuit containing V sub I and R1, we get V1 is simply negative V sub I. And we can just equate this V1 and this V1, right? So this is equation number 1, and here we have equation number 2. Equation number 2. So equating equation number 1 and equation number 2, we get negative R1 over R1 plus R2 times V naught is going to be negative V sub I. And this negative disappear. All what you get is V naught over V sub I is going to be R1 plus R2 over R1, which is basically 1 plus R2 over R1. So therefore, voltage gain of non-inverting op-amp AB equals 1 plus R2 over R1. And that's the final answer. Okay, I got this voltage gain this way. Okay, so we actually analyzed the circuit completely from scratch, and I showed you how to assume. What I did, I have a little bit different way of solving the circuit to find the same gain. Okay, but here I typed it. So in the scribing, I want you to put this solution, step-by-step derivation here that I have, plus the one that I went through. Okay, you will understand this. See how to analyze this op-amp circuit. So what you have here. So I gave you this little circle here. Circle 1, circle 2, circle 3, circle 4, circle 5. Which means you follow this step. Step 1, you assume that the voltage difference between these two terminals is going to be 0, which means that this is virtually short. This is virtually short. Virtually short. and then no current, this is going to be 0, this is going to be 0, no current flowing here. And then step 2 input voltage relation. Step 2, I mean this point and this point, they have the same voltage. So therefore voltage at this point is same as voltage at this point. So Vi2 is same as Vi, and Vi1, which means that voltage at this point is same as Vi2, which is Vi. So because of virtually short, because these two terminals are virtually short, voltage of this point is same as voltage of this point, which is V sub I. And then number 3, voltage divider at inverting input. So now what you can do, because no current is flowing, voltage divider, so it is going to be voltage source here, V0, R2, R1, they are connected in series. You find the voltage divider, which is V sub I1 is simply voltage at this point is going to be voltage at this point is going to be V0 over R1 plus R2, and substitute Vi1 equals Vi1 equals V sub I, so you get this relationship, and closed loop gain is going to be V0 over Vi is 1 plus R2 over R1. It is a little bit slightly different way of analyzing, but you get ultimately you get the same result. Now, voltage follower. You have seen the op-amp, and this voltage follower circuit was in the lab handout that I gave you. Did you see that, guys? Did you see this circuit? In the lab handout, we have that. I say, before you start part 1, I say, check the circuit, you check the op-amp using voltage follower. Okay? So you use this voltage follower to check your op-amp, whether your op-amp is functioning properly. What you could see, what you see here, guys, look. So here output is simply 1 plus R2 over R1 input. Okay, guys, look, if R2 is 0, substitute R2 equals 0, which means that R2 is a simply piece of wire. R2 is a simply piece of wire, which means it is a piece of wire like this. You see that? So there is no R2 here. You just replace R2 with a piece of wire. Okay? And then non-inverting terminal you connect it to the input. Now this R1 you just take it out, keep it open. R1 is infinity. So R2 is 0, R1 is infinity, which means that it's an open circuit. So 0 over infinity is what? 0, right? 0 over infinity is 0. So 1 plus 0 is 1. So 1 times Vi is going to be Vi. So output is going to be exactly same as the input. So you convert the non-inverting operational amplifier to an unity gain operational amplifier, voltage follower, which means that the output is simply following the input. Output is simply following the input. Mathematically, you see that U0, which means piece of wire, over infinity, which means that there is nothing here, no connection. R1 is absent. Okay, R1 is absent, which means that it's an open circuit. Open circuit means that the resistance is infinity. Okay, so resistance is infinity. When I have two things here, I have two conductors here, and I supply voltage here, and I have another piece of wire, and there is nothing in between, which means that there is a resistance. Ideally, that resistance is infinity. It's an open circuit. So, so R2, I simply removed it, making it infinite resistance. So 0 over infinity equals 0, plus 1 is 1 times V sub I is simply V sub I. So therefore output is going to simply follow the input. So that's exactly what I said. In that case, your voltage gain is going to be 1. The voltage gain is going to be 1 because this operational amplifier has voltage gain of 1, it's called unity gain amplifier. And you do not need any resistance or anything. So what you can do, you can take an op amp, immediately you can check whether or not this op amp is working. So if you put a sinusoidal signal here, so you get exactly the same output on top of each other. So you simply connect output to the inverting terminal and input to the non-inverting terminal. And you see, you take the output from channel 2 of your oscilloscope, output is going to simply follow the input. Okay? So it is called voltage follower. And why we need voltage follower? So one application I said that I use this voltage follower to test my operational amplifier IC. I just wanted to see, first I checked whether or not all my operational amplifiers, each IC has 2 operational amplifiers, right? The IC that you have used, guys, each IC has 2 operational amplifiers. Immediately what I do, I put DC power supply and then check sinusoidal sinusoidal signal as the input, I see the output. If I see the output in channel 2 and input in channel 1, I see that they are going to be on top of each other. If I see that, that means that op amp is working. So this is a simple way to check an op amp, unity gain amplifier or voltage follower. I have this in the lab manual as well, and it is voltage follower is ideal for signal isolation, impedance matching, due to its unity gain, because we don't want to lose anything. High input impedance and low output impedance. So these are some applications. Now, what you do, you include this exercise in your scribing report. Exercise 2.9, exercise 2.11, and 2.9, 2.11, 2.12, 2.13. Go through all these exercises. So if you understand the theory here, the way I derived those exercises, author has given the solution as well, the answer, okay? So it should be a piece of cake. So make sure you include this in your scribing. Group 40, it goes cuts on the it's the first time, right? Yeah. So I'm going through this slowly, and in our chapter 5, chapter 6, so what we are going to do, we are going to break this op amp, okay? We are going to break this op amp and we will see what's inside this op amp, which means that all the transistors, MOSFETs, they are inside this op amp. Okay, so we will look, we'll simply zoom in and see what's inside this op amp, and we'll study transistors. Do you guys have any questions so far? No? Was it clear? You guys have space?
What's impedance matching?
Oh, impedance matching means your output power has to be maximized. Okay? So whatever source power you have, you get, let's take a simple example. Maximum power transfer theorem, have you heard of maximum power transfer theorem? From 240, you should have heard maximum power transfer theorem. So impedance in general, it could be like with capacitor, it could be with inductor, right? Could be with resistance. It's not simply resistance. Impedance matching, you match the impedance in such a way that the output power is maximized. In other words, if I look at a maximum power transfer here, so you get a power generated from Niagara Falls, for example, okay, and you get the power right from here, okay, and in between you see bunch of cables, right? You see the bunch of cables. So we want to transfer the maximum power to the load. So therefore we match the impedance, all the impedance that we have, impedance of the source and impedance of the line. So source impedance, which means that all the circuit diagram that we have in Niagara Falls power station, and then the line resistance or impedance that we have. So these two impedances have to be same. So if you have these two impedances, then you get maximum power delivered to the load. Okay? So impedance matching is very important. And also this antenna, who are taking, you guys are taking two-way, you took two-way, right? So Dr. Shastri probably talked about impedance matching. So antenna, if you, if he didn't talk about it, impedance match antenna in two-way, you would probably talk about impedance matching in his antenna course. Antenna 451, 551, or 452, 552. So there you see that antenna, when it is an antenna, it's all about impedance matching. So it's 50 ohm impedance matching. And in fact, look at the function generator. You guys know function generator, right? You know function generator, and right under the function generator connector, BNC connector, right after that it's written 50 ohm, which means that impedance is 50 ohm there. So impedance has been matched to 50 ohm, so that the power that you get and the output of that BNC cable, BNC connector, is matched with the is maximum with respect to the power generated from the source. Is that clear? So in all, the purpose of impedance matching is that the power that you get has to be maximized. If impedance is not matched properly, which means that you do not get maximum power. As simple as that. Let's put it this way. Okay? Clear? Now, difference amplifiers. The word actually says. These amplifiers will amplify the signals that are different between two inputs. The name says it all. These amplifiers will actually amplify the signals, will amplify a signal that is the difference between two inputs. Now, where do I, let me talk a little bit about it. I have some description here, okay? But let me talk a little bit about it. These difference amplifiers, you guys work with sensors, right? A lot of sensors, so some of you are building robots, and you see that, now you have sonar sensors, and sonar sensors come with some, electronic board, right? Okay, and these sensors pick up very, very small signal. Those are voltage signal basically. When it senses distance, for example, the output voltage of that sonar is going to be proportional to the distance to the object. Okay. Now, these signals are basically the difference signals, and these signals, what we want to avoid when the manufacturers, they actually build sensors, they want to avoid noise. They want to avoid noise which is coming from the common inputs, okay? Which is basically the common signal between two inputs. and those common signals are usually noise, and we want to reject those noise. We want to reject those noise. So to reject noise, we want to use difference amplifier. Okay, to actually reject some noise, extract small signal, original signal, but we want to reject some noise. Of course, we'll be using some sort of filters. There are many other filters, but initially we want to first get rid of the signals that are common to both inputs, and those are considered as noise. So we want to get rid of noise, right? So it's that simple. We want to get rid of noise. So these difference amplifiers will amplify the signal that is the difference between two inputs, and will reject signal that are common to both inputs. Let's put it this way. And the signals that are common to both inputs are considered noise, and we want to reject those noise. Okay. So here we have two inputs. Here we have input 1, and this is input 2. Input 2. So VI1, VI2. This terminal, this 1, 2 represent input number 1. This is input number 2. These two inputs, please pay attention. What is the purpose? So these two inputs are coming from sensors. These two inputs are coming from sensors. Now, what we want to do, we want to amplify the difference between these two inputs. We want to amplify. Is that simple enough, guys? So we want to amplify the difference between these two inputs, but we want to reject the noise that is actually coming from the common signal of these two inputs that are common to both inputs. So therefore, these two inputs can be written in two different components. One is the difference. So this is basically differential input. So V, I, D. I for input, and D for difference. Okay? So VID means input difference, and in formal term we call it differential component. So VID is the difference between two inputs, which is VI2 minus VI sub 1. So we have the differential component, and we have common mode component. VI, V input, CM. CM stands for common mode. V input, common mode. So VICM. VICM. I is coming from input, and CM is the common mode. So VICM is the common mode signal, is basically summation of these two inputs divided by 2. So these inputs, the main idea here, these two input signals that are coming from sensors, for example, these two inputs can be represented in terms of two components. One is called differential component, VID, V input difference, which is the difference between these two inputs, and VICM, V input common mode. V input, VICM, I is coming from input, I from input, and CM common mode, from common mode. So these two inputs can be written in terms of these two components. And when you draw the circuit diagram, when you build these two inputs, you can actually represent this, you can just think of these two inputs as one voltage source, which is the difference component divided by 2, and another voltage source like this, which is difference component divided by 2, and another voltage source here, which is the VICM, which is V input common mode. Okay, so these components, once you have these components, actually you can, these two equations you can solve for V I sub 1, V I sub 2. You can actually represent all these two inputs in terms of VICM and V common mode and differential component. The main idea here is the practical operational amplifier gives the output voltage. This output voltage is going to be the gain of the differential component, differential mode gain, and common mode gain. So this is the common mode gain, and this is the differential mode gain. In practical circuit, guys, in practical circuit, we want differential gain, but we do not want the common mode gain. Okay? Ideally, this common mode gain is 0, has to be 0, but it is not 0. But we want to get rid of it. So when you see the operational amplifier, guys, when you see the data sheet, if you open the data sheet of an operational amplifier from Texas Instruments or analog devices, when you open this data sheet, you will see there is a term called common mode rejection ratio, CMRR. You will see a term called common mode rejection ratio, CMRR. This common mode rejection ratio, it's 20 log the magnitude of the differential gain over the magnitude of the common mode gain. So if you see, you will see some number. And more, how do you evaluate the quality of the operational amplifier? How do you know that this operational amplifier is doing good job? Okay, this difference amplifier is doing good job. You just look at this CMRR, and CMRR is provided by the manufacturer for each op-amp. So you look at that, and this CMRR is in dB, and more CMRR you see, better than op-amp. Okay, so here higher CMRR, common mode rejection ratio, better rejection of common mode noise. So the noise that is common to both inputs, we can reject those noise if we have higher CMRR. Okay, common mode rejection ratio. So I'm not writing it here, I explained in my slide. Please annotate my slide and also just rewrite what I have here in your scribe. Now let's apply this theory in a practical difference amplifier, which is using single op-amp difference amplifier. So try to understand this circuit, because next is coming, even the complex one is coming. See, instrumentation amplifier. Okay, so you will see a lot of instrumentation amplifier. You see the complex circuit is coming, but this part of the circuit, this part of the circuit is exactly what I'm going through now. Okay, so the problem here, we want to find objective. Or goal. Goal here, we want to find what is the output voltage, what is the output voltage in terms of certain gain times output voltage, so V I2 minus V I1. So this is the difference input. this is the differential gain. So this is equals what? We want to find that. And difference input, this is given. Difference input given and differential gain. Find it from resistor network. Find it from resistor network. Okay? So we will see how to find it. So what we have here, from looking at this circuit, you see we have 4 resistors. R1, R2, R3, R4. There are 4 resistors. 2 resistors are connected from non-inverting input, and inverting input is connected to input V sub I1 through resistor R1, and there is a feedback R2. Now, there is a condition for this to operate as a difference amplifier. I'm not going to go through the proof. There is a condition that this ratio has to be same. So R4 over R3 has to be equal R2 over R1. So R4 over R3 equals R2 over R1. This condition has to be satisfied. In other words, R4 over R3 plus R1 times 1 plus R2 over R1 equals R2 over R1. If you simplify, you will see you will end up with this condition. Now, here I have the derivation. Step 1. Step 1, what you do? Step 1. You make it 0. So which means that you just substitute it with simply ground. It's grounded. Okay, guys, tell me. These 2 terminals, because of the feedback, these 2 terminals are virtually short, right? Right? That's what we have learned. These 2 terminals are virtually short. How much current going through this terminal? 0. How much current going through this ampere? Through this terminal? 0. No current. Okay. But these 2 terminals are virtually short. Okay. You tell me. Here, I put 0 here. This input is 0. 0 current is flowing. What is the voltage? Here I have 0 voltage, it's grounded. I see that 0 current going here. What is the current flowing? 0, no voltage here, guys. It's 0. If 0 current goes here and no voltage, don't you think we can just omit this and we see that the voltage here is going to be simply 0, right? Right? Voltage here is going to be simply 0. Don't you guys think that we can simply get rid of this and we can simply put the ground right here, right? And this happens because I said that Vi2 equals 0. Clear? Now look. So I have this. I just need to make you understand. So I have this. Look. So V sub I1, and we have R1 here, and then negative, positive, and this is going to be 0 ground. and this is output, and this is output V naught. Okay, are you familiar with this? This op-amp, what is this op-amp? It's an inverting operational amplifier, right? So inverting operational amplifier, we know the output. The gain is negative R2 over R1, right? Right? So the output, and because I activated only one input, so let's call this VO1, which is simply negative R2 over R1 times VI1. See, I deactivated one input, replaced it with 0, and I have only one input activated. So I have corresponding output. And so if you write it down, I also have these in my slide here. I just need to understand. So here, output due to inverting input Vi1 with Vi2 equals 0 is given as such. Okay? But here I just make sure in the scribing you include these guys. So I simplified the circuit. I actually, for you to understand, I put here 0. Grounded. Non-inverting terminal is connected to ground. But here in my official slide, I did not put 0. I did not put ground here because I know that its voltage is 0. So you can think of this as ground. Okay? So that's why we have one input activated, and we see that the corresponding output is this. Similarly, now you put this guy. This guy is 0. If this guy is 0, look, this guy is 0. The input is 0. This guy is 0. R1 is 0. This is negative, this is positive. So this is R2. This is V on. Okay? Now look. This is going to be 0 ampere. This is going to be 0 ampere. Okay? And this is virtually short. Look, I have the second input activated here. Do you see that? The first input I put 0, second input is activated. Do you see that? Second input is activated. If second input is activated, don't you think that there is a voltage divider here? So Vi2 and R3 here and R4 here. So therefore, the voltage here is V plus. The voltage at this point is V plus. So this V plus is going to be simply R4 over R3 plus R4 times Vi2. Now we have the voltage at this point. Now we can just simply replace this with V positive. We can just replace this with V positive. Okay, are you familiar with this configuration? Our class started with this configuration. Today's class started with this configuration. Do you see that? Do you see that? It's a non-inverting operational amplifier configuration. And I know its gain. Right? So I can directly write this gain. So I can directly write this gain. So in that case, all what you have here, V out 2 is going to be when the other input is deactivated, V out 2 is going to be simply 1 plus R2 over R1 times V plus. And V plus is I found it using voltage divider, using the input right here. Now, you guys learned superposition. Don't tell me that you don't know what is superposition principle. So in 240, you guys learned superposition principle. Yes or no? Superposition principle. Basics. You guys know Thevenin, Norton, mesh current analysis, node voltage analysis, superposition. No?
I feel like we learned that, it's not exactly.
The superposition principle, this is also another technique. Thevenin, Norton, mesh current analysis, node voltage analysis, and superposition. Very important. In electrical engineering, if you guys do not know superposition, it's a big problem. Superposition principle, what it says, superposition principle, what it says, that if you have open application, superposition principle. Superposition principle. Please write it down. Superposition principle, let's say you have a linear system and we are working with linear circuit. Linear system or circuit. We are working with linear system. Okay? So linear system means that output follows linear straight line relationship. Okay? So you have linear circuit. Now, if the input is, let's say I1, you get output Y1. Same system, same linear system, let's say input is I2, you get output Y2. Okay? So you get, for input I1, you get output Y1, for input I2, you get output Y2. What you can do, if you simply put input I1 plus I2, you can close your eyes and you can say that because it's linear system, output is going to be Y1 plus Y2. Okay? And because it's a linear system, if you multiply with A here, B here, output is going to be A here, B. That's what superposition principle is. Okay? Mathematically. Now we applied this superposition principle. We applied this superposition principle. So we deactivated one source at a time. So we activated one source at a time, and then using superposition principle, we get the overall output. So the overall output is going to be summation of individual outputs. So the overall output is going to be summation of individual output. So I did some math a little bit, and then we applied the resistor ratio condition. That way you get the output voltage, which is R2 over R1 times Vi2 minus V1. So this is exactly what I was talking about. Which is output is some gain times the difference between two inputs. And this gain is basically R2 over R1. This gain is simply R2 over R1. And which is basically R4 over R3. It's the same. Because we have the resistor condition. So R2 over R1, R4 over R3 has to be R2 over R1. So this condition has to satisfy. and your differential gain is R2 over R1. So R2 over R1 times this input. This is what we have. So important remark: the difference amplifier rejects common mode signals effectively if the resistor matching condition is satisfied. So we have to make sure the resistor matching condition, which is R3 over R1, R4 over R3 equals R2 over R1. This ratio has to be set. Like that, your difference amplifier will be able to reject noise effectively. If this resistor network does not satisfy this condition, this difference amplifier will not be able to reject the noise, common mode noise effectively. So as a designer, you need to make sure that this ratio, this resistor matching condition is satisfied. Make sure you go through this exercise at home, 2.15 and 2.16. So it is 2.15, 2.16. Okay? It is 10:15. Any question, guys? No? We have a quiz? Okay, when is our next exam?
I don't know. We're actually there.
So I changed the date of our first exam. Yeah, lab assignment number 4, I'll be posting here. And our first exam is next week, right? Right? So we are right here. And first exam next week, we are still in module 2. So 1 days. Okay, alright guys, thank you. I will see you on Thursday.